In a laboratory setup, we showed some relativistic behavior. Relativistic dynamics happen at the speed of light, but we could mimic them using the quantum qubits, quantum algorithms. Now, if I do it in large scale, then I should be able to mimic some of the strangest, the most complicated, or the highly fascinated things like black hole, or we call, I don't want to use the word like time travel and few other things, but because there is, but of course, everything which quantum physics defines, the most complicated to the edge of what we understand in the universe, we should be able to mimic them at some point. And that is what I see might not be 10 years down the line or 40, 50 years down the line, our future generations will accomplish with the most complicated quantum machines being built.
Thank you for joining Once Changing the World. I'm your host, Eddie Avil, and today I have with us Professor C.M. Chandrasekhar from the Indian Institute of Science, Bangalore. His team recently achieved a pioneering milestone by building India's first 6-qubit photonic quantum system. This breakthrough places India amongst the elite group of nations leading in photonic quantum computing, a field that leverages the quantum properties of light to pave the way for next-gen computing with immense potential in medicine, artificial intelligence, material science, and beyond. Today, we dive into the science, challenges, and future of photonic computing and the role of India. So, Professor, really appreciate you taking time and being part of the podcast. Now, I've been deeply fascinated by quantum physics, and I believe the entire world is quantum mechanical. You, me, the trees, the air, anything and everything. So it's so beautiful. And the deeper you kind of dive into it, it seems like a rabbit hole. I wanted to start with you. What first drew you to quantum physics and quantum mechanics? It will be great if you could possibly maybe also explain my audience what quantum physics and quantum mechanics is, and how has your understanding evolved over the years of both quantum physics and quantum mechanics?
Yeah, thank you very much for this meeting or like interview which you're hosting. It's a great opportunity to try to talk about quantum physics and give an idea of where we are heading towards technology. So it's a journey from high school, I should say. Physics, right? Physics itself fascinated me quite a lot. Trying to understand the way the world is around. Like you started out rightly today, everything is quantum mechanical around you, but that was not what as a school kid we began with. It was something around you, and you just want to understand them. The more and more you try to understand them, it is the classical physics, it's electromagnetic theory, it's atomic physics, and then you just hit a right bottom there where there is uncertainty and quantum mechanics, and they all logically connect to the world we are living around. And that's a long journey in a very short word. It's literally the way the nature works around you. That's what fascinated me. Right? The deep well into understand how things work around you. It can be a small pens, ballpoint pens, ink which flows towards the way the light from the universe which is reaching us, and understanding the dynamics around that. And when you start looking at them, it opens up a whole lot of challenges. And then you start picking up what you like. It's just like you have so many things around you. You start liking some color, and then you pick them. You start having a collection of them, and that becomes your zoo to play around with, right? So for me, it has been a journey like that. It's a physics. From physics, you started learning the statistical mechanics to electromagnetic theory and astronomy. I think as a kid, astronomy is also one of the things which everybody gets fascinated by. You see light. So light is something which really, fascinated. From then you start understand them, learn some math, and that's how it has been, a journey to quantum mechanics.
So, Professor, I think it was 1801, when Thomas Young created that experiment, the double slit experiment. I think it's one of the most fascinating experience, but you still can't wrap your head around it. What's going on? So, it will be great if you can the double slit experiment, and what does this experiment say about our world?
Yeah, so it's a very we can go back to Copernicus also, right? Where everything is granular or a particle nature. The light itself was initially treated as particle, right? So first it was particle, and then it was the wave theory which came in because people could see some interference. So now that kind of explained a lot of classical optics, which people try to look at it. So what Young's experiment says is that, or like double slit experiments in a quantum picture says is that you can, if take a two slits, you send light. So but of course, there are a lot of internal details that the slit should be separated, with a certain width. So now if I send a light, then it has to take both the paths. If it takes both the path, the moment it comes out, there should be some interference, just like a water passing through a weight, and then they can have an interference. But if it is a particle, then it has to go through one of the slits, right? So it can't go through both of them. So if it's going to one of the slits, then you are not supposed to see an interference. So now, if I do a double slit experiment, then it should clearly tell me whether the light is a particle or a wave. Right? So that was a clear kind of, I said to pass which theory is correct. So this was a thought experiment. But then, depending on the conditions the experiments were done, or like, were thought about it, both would pass. When you are trying to see, when you're not trying to see where the photon is going through or where the particle is going through, then it's just behaving like a wave. But if you're trying to see its trajectory, the way it passes through, then it's behaving like a pattern. And you can actually observe both a wave behavior or a particle behavior, depending on the observer's way of looking at it, right? So that's kind of really, brought down to a practical reality of the world we live in, because that's what we understand, that's what we observe, and we have to accept it, or we have to come up with an alternative theory. Right? So that's where it stands, right? If you don't accept what you are observing or what you are trying to see, then I need to build a new theory to make it explain. So is there something which you can do both? And this what puzzled many people for like 2 to 3 decades during the formulation of quantum theory, right? So, but then the mathematics as a tool tried to help, but you assume there is some uncertainty. There's a wave-like behavior with every particle associated. Now, it's also sometimes wrong for me to say, okay, it's an oscillatory particle or something, because then again, I'm defining some boundary conditions for them. But what we have is that we know what we begin with and we know what we observe. So now we need to build what could have happened in a logical construct. So might be intermediate time, we measure certain things and we observe them. And our theory, we model as to explain the whole process of it. So then it has been now a lot of experiments have been done. Now today we are building technologies based on it. So which means that it's a wave particle duality. I can exploit either wave behavior or a particle behavior. So that freedom I'm getting. If I'm just taking any classical, it's cricket ball, I can only treat it as a particle and I can only use what all it can give me as a particle. If I take water or something which has a wave behavior, I can only extract the positive things or like resources which can come from a wave nature. But if I'm taking a particle which behaves quantum mechanically, then I can choose both of them. When I want a particle behavior, I can choose. When I want a wave behavior, I can choose. So it's coming as a dual resource to me, right? So that's literally is what we are exploiting today for quantum technology. Can I exploit both wave and particle behavior simultaneously? Of course, that comes in a more intricate level, but on the bigger picture, this is what we are trying to do. And that is what is leading us, both these things together, that is what is leading us what we call as quantum resources, where superposition, interference, entanglement, these are the key things which are using for technology. But this is origin for all those big resources which we talk about. Right? So
so very interesting, because this experiment proved the wave particle duality. And it's so very confusing because in the macro world, things are fine. But as soon as you go into the micro world, things starts getting like slightly.
no, I try to put it in a slightly more different way. It's not about things are dramatically changing. It's just that there is a transition, which we fail to understand when I know it's up to, because at a microscopic scale, wave behavior is not prominent. Right? That's what I would say, right? So, for example, there is a very simple high school physics where we study the velocity is proportional to the temperature, right? And there is also de Broglie wavelength where which try to see an atom or any particle. So there is a wavelength associated with certain temperature or something. So wave behavior associated with it. So when you're trying to think of a bigger particle, or like when the temperature is also very very large, wave nature becomes very insignificant. That's how we are seeing a particle behavior here. Now the subject of when the quantum particle transfers to a classical behavior, there's a very there's no clear boundary line. That itself is a topic of interest. But of course, we do see both the ends very clearly, and there is a transition which is happening. So when things are at the atomic scale, when I'm talking about electron, photon, or atoms, both wave and particle nature predominantly are there. But the moment the sizes, many atoms are put together, so what happens is that there is the interactions between them, and there's a constructive, destructive, behavior which happens, between them, and then the wave nature diminishes. We don't see the wave. It's almost like when I talk about when I'm seeing sea waves, there is a clear, if there is a pattern associated with it, I get a very prominent constructive and destructive patterns, right? So there's a waves which flows down. But the moment you have a lot of disordered, interactions which is happening, then everything cancels up and you see like a smooth surface or something, right? So that's also possible. That's how we start, no, seeing the particle behavior very prominently when you go to the classical, bigger scale, and wave behavior is very insignificant. We can't detect it.
So what you're trying to say is there's somewhere in the middle, there's some kind of a transition which
Yes,
is
yeah. So
happening, which
yeah. So it's what we call as classical to quantum transition is a topic of its own interest, where we see there is a noise associated with it, and we make the world interact, and whether that is what is destroying the quantum behavior. When I say destruction of quantum behavior, which means that we are trying to diminish those dual behavior and trying to get to particle nature, which you see in the classical world.
right. No, Professor, in the quantum world, there are a lot of things which is happening, which one might call a term weird. Like, for example, the quantum superposition and the entanglement. For someone who's new in the field, who doesn't understand this, can you kind of explain it and break it down, like what quantum superposition and what quantum entanglement is, and how does this play a role in the quantum?
Yeah, weird is a word which probably commonly, but for us, it's a very, fascinated picture of the world, the amazing feature which you see in this whole universe, right? So, okay, the superposition in a text. Okay, let me first put it as a textbook definition point, and then let's try to understand, right? You can have a single particle, either it's a photon or an electron or anything which we call a subatomic, exist in two places at the same time, right? Now, that is what we call as a superposition. Simultaneously, it can be in two places, but two is the most simplest way to put it. When we are trying to exploit it at the larger scale today as a technology, it can exist in superposition at multiple places, right? So that's what we call it a superposition. Now, how we can understand superposition as a simple level is like now we have to bring in a wave behavior, right? When we talk about the quantum at a smaller level, they have a wave behavior, which means that now wave is spread around the given position space. Now, how much it spreads depends on the environment around it, right? So it can be like something can be destructive. You may not be able to spread it for a longer distance. It's almost like expanding your bubble gum, right? Or like you have some elastic you need to expand. It's just that way. If the particle can be spread in superposition. Now, the moment I look at it, then it collapses. It's almost like you're trying to force something is you're trying to intervene to see where it is. then it's like, when we say Mercury was like a ball and it just at such one particular place. So it ends up being at that place. So you can make it spread. The moment you're trying to observe, it gets identified. So this is what we call as a superposition. Now you can control how you can bring them in superposition state. This is to do with a single particle. So, can one particle be at two positions simultaneously? It's a very big puzzle which people are trying to look at. Even today, there are certain questions which, at the foundational level of quantum mechanics, we try to address how much non-local it is. Like, can a single particle be in two different places, and how do we clearly establish that they are, and what are the full what you call foul proof measurement or methods can be used for it. So now that's as a still in topic of interest, but as a as an established one, they are very clear that you can have them in superposition in multiple places at the subatomic level as single particles. Now entanglement is a next level of it. So which would mean that can two particles be in superposition state? And that's what it would mean. Like, now, which means that I can have two particles and I create some kind of superposition of those two particles and then send them into two different places. Now, no, it can be some properties. It's not like, I take a property like polarization or something like that. If it's a photon or if it's electron, the spin. So then I can take them apart because when I'm trying to create them in superposition, they would have some interactions. When I move them apart, the state of one of them would end up telling what is the state of another one. Like, I don't have to even make any, I don't even have to ask what it was. Now, this is like violation of Einstein's theory of relativity, speed of light transport. And that's how Einstein did not want to believe something like this really existed. He called there's some spooky action happening there. There's something hidden variable which is really doing it. But it took a lot of time for people to come up with an understanding of it and do experiments and verify. But what that's a reality. So you can actually, but is it easily creatable? No, it's not. And you can't create entanglement very easily. It's very hard. But you can bring two photons together or like you can actually generate them in some specific manner such that they are entangled. Then you can take them away for thousands of people are actually dying for thousands of kilometers, and then measure polarization in one of them and instantaneously say the other one should have been a different polarization. So it's like instantaneous information exchange, and that's what entanglement is about. And uh, every labs in our lab, we keep generating entangled photon pairs on a regular basis. And every time you do experiments, you know that you're seeing it happening in front of your eyes. You're measuring, and then you have to believe that's how nature can. That's what nature has to offer to us, and that's what is helping us to build the resources. I think in between these two, a superposition and entanglement, which is there two particle, there is an interference which comes into an important role. We're just trying to help us to create a transition of the single particle superposition and many particles interference, or even single particle can interfere. That's there because it's what we explained about double slit experiment. It's like a single particle which goes because it's a wave behavior. It actually takes both the parts, and then when they come out, there is an interference there of the single particle, right? So now I can even think of many slits, right? The first is two slits. The next one can be a four slit, and the next one can be a six slit. Now the one particle which is actually taken two parts, the next time it ends up taking all those four parts in superposition, it can end up giving a completely a different form of interference at the end. Now, that is what we use as a reference points to build our algorithms today. Quantum algorithms are a kind of, such kind of interference behavior. Now, there can be a constructive, if you can engineer how the slits are made, right? I can make some slits missing and I can have some slits slightly wider, some slits, I can engineer my slits. If I engineer my slits, then I can define where to have a maximum interference, constructive interference, where to have destructive, okay, no interference at all, right? So I can engineer them. Now that is all. It's actually my algorithms. The where I get my constructive interference is my solution to the problem. That is how we do quantum computation itself. It's almost like engineering your paths for photons or electrons or qubits, whatever it is called. Superposition is what is defining our qubits. So when we talked about superposition, being into slits together, is like having two spins up and down simultaneously together, and that is what is mathematically what we call as qubit. So engineering superposition of but as a single particle would be like controlling my qubits. Now that is how we map the fundamental physics, a simple double slit experiments becoming multislits, controlling their dynamics is almost mapped to the way quantum computers are engineered at a very elementary level. Now I can have many particles. I can have large number of slits. I can make them interfere and engineer them in different way, and that leads into a very complicated problem. And that the solution, what I measure, is my solution to the problem. It can be a computational problem.
Want to get into the quantum computing side, but before that, the current computation paradigm, I mean, that's been is the binaries, which uses zeros and ones, and for this current computation paradigm, what we use are these silicon chips, the silicon chips which are powered by electrons, doing all the computation passing through these wires. Now there's a saying that that Moore's law is reaching an end, because now we are kind of pushing around and creating these chips which is beyond like the 2 nanometers. I mean, there are these 2 nanometer chips that we have created. Eventually, I mean, the quantum effects gonna and then maybe it's going to be the end of the Moore's law. What are your thoughts on that? I mean, is that current computation paradigm going to end because we won't have any space to kind of engineer more transistors into these chips? That's the first question, and then the second is photonics the future? Will photonics play a role, and will also be great if you could maybe explain photonics and
Yeah, I'll try to answer the first question. And I said, so Moore's law was not an experimental, obtained conclusions, but it was an observations over years how your transistor sizes are changing and how your computational powers or how many transistors we're putting. And that clearly said that if you're trying to double the transistors in your chips which you are building or in your silicon wafer, it reaches a stage where you are getting into a nanometer scale. It is which when one in the beginning, what I tried to say was that if things are bigger, your particle behavior is very very prominent. The moment when it's becoming smaller and smaller, wave nature also gets prominently visible. Now that's what exactly is what Musla is also trying to take us to. Like you reach a stage where you have to put your transistors or your operational classical bits devices at a size where wave behavior is getting prominent. The moment wave behavior is prominent, then first one to the next one, there is a over, spread of the waves. So the moment you have spread of the waves, your classical bits or your information operations, everything gets mixed up. So now you need to maintain a size where you're not getting to a limit where wave behavior starts entering into your picture. That means a quantum mechanics starts coming to play a role. So that's what it said as a limit. And then they said, if you want to go smaller than that, then you need to operate at a quantum mechanical level. Or else you can't, you should stop thinking going beyond that. That's what is most of it. But I think these were all an initial ideas which were put out to say why one has to start thinking in terms of quantum dynamics. But I think much more fundamental here is that why we do computation or why we do anything at all, right? It's a binary. Computers was a language which was developed for us to make things easier, right? So might be or to make it automated or like to get something. 2 by 5, I know I can just write it as 10. 2 into 10 is 10 for me straight away. 2 into 5 is 10 for me as a straight away calculation. But if you ask a computer to do, it converts into binary terms and then it adds it and it gives me it reconverts well. But it's still a good language to begin with. And now this was a mathematical evolution which happened for us, and we got a tool. But now, if you see how nature is doing all these things for us, certain things are very naturally happening in nature, much more better than the way the computers do. It's because nature is much more efficient. What are laws of nature? If we all agree that we are no, none of us have come up with any law better than quantum mechanics today to explain what is happening around the world, and it's hundreds of years, 100 years now. Every experiment and everything which has been done has only made sure that that is correct. So now if we use laws of nature and build, might be we'll be able to do far, far beyond than what we even think of today, right? Now, today we might be talking about few things what quantum computers can do. But if we are trying to understand nature and mimic nature to the best of its possible, then what can open to us might be much more wonderful than what we think about, right? So I think that's probably is much more, important than Moore's law. Moore's law is a very engineering statement to say why, we have to go for a quantum computer. But whether it's not about economics for me. I mean, why? If you ask me why I'm interested in quantum computing or why it's quantum, nature is doing that. To understand nature. Let me try to do, and that itself is, in fact, Feynman's statement also in inviting people to do quantum computing was that, see, if nature is doing, or if I want to even mimic nature, I need to follow its rule. Only then I can mimic. Others, I will only be able to do some approximation of it, and that's what I see is a driving force for most of the physicists who are working in quantum computing or quantum information as such. That's the first part of it. Now, I think the second one is a much more interesting question, which I may not give you a very an answer which would say yes, photonics is a future, right? No, I'm not going to say no, because we don't know. Because there are two things. One, we definitely know quantum theory is what is defining everything. And if you look at the current scenario across the world, any researchers, people are working on all possible platforms to build quantum computers. When I say platform, which means that when I mentioned about superposition or entanglement or interference, now which are the natural or nature's tool which is helping us to control these three features, right? It can now be a superconducting qubits, which is one of the promising candidate where you can actually create superposition. You can see some interference. You can also have entanglement, so which means that you can actually do some computations with it. Photons are there, which is fantastic. Gift from nature for us to play around with. And we have atoms. For decades, people have learned to cool atoms, trap atom in one particular position, control their quantum behaviors. Ions are there. These are all, clearly, there are about six of them, which is now very, very an important candidates for qubits. Now, all of them have their own advantages and a big disadvantages. Right? There is a big hurdles which each and every hardware has to pass to have our dream machine built. Right? So we don't know. I mean, as researchers, for us, we know what all are the positive, and we also know what is the hurdle which has to be crossed. And we believe that we probably can jump that hurdle, and there will be some solution to overcome that hurdle. It's true with everything. I can just give, in the interest of time, I will just give an example for two of the prominent ones these days, like on, photonics. The positive thing is that it doesn't interact with the environment, so it's that you can actually make them go control how photons can move around. Wonderful tool, but because they don't interact with other photon also. Which does not help me to control the gate operation. What we call computation means you need to do some interaction operations. You can't make them interact the way you want, and that is one of the hurdles. Or else everything is fantastic. I can generate photons. I can, make them move around the way I want. I can measure them. It can be done in room temperature. But how to make interactions between them is one of the hard problems to be looked at it. Now, if I look at superconducting qubits, they are, not at the single atom level. It's a macroscopic atom. You can create superposition. You can do some kind of interaction and everything. But now the problem with them is like, I have to now keep all these qubits built, and then now all these qubits are a macroscopic item. So they generate their own noise, and those noise, the moment I am having some few hundreds of qubits built, is making the system lose the quantum behavior. It's decoying them. I can actually, I don't think, it's very hard task. You can have thousands of engineers and build few thousands of qubits of superconducting system. You can build. Now, can you make them work coherently without having a noise? Is a big challenge. It's a scientific challenge there. It's not just about a technological or a translational problem. We know, we are aware of it. Researchers who work on it are aware of these problems. But now, only when we have problems, we can solve them, right? And there's no reason why one can't solve it. Again, there is no any law or theorem which says there is no go beyond it, right? So it's a task on us to find out solutions for them. So having said that, I'm going to say that there is no clear winner right now. All of them are very good. And for next, I mean, I strongly believe that for next 1, 2 decades, all of them will be a very important players. I would say just we are creating a massive knowledge base right now, and probably that's going to be for next decade from an academic point of view.
Right. Professor, thank you for explaining it so beautifully. I think we're living in such a fantastic point of time. I think the current classical computing paradigm, it's completely upended our world. And the kind of applications that it's given us, it's like it's super awesome. It's completely changed the world. And here we are at the cusp of maybe transitioning to a different paradigm. And you rightfully pointed out, I think nature is quantum mechanical, and there we are going over there and possibly kind of, trying to build a computer which plays with the source code of life, atoms itself, and when we are able to build machines and quantum mechanicals, whatever approaches you take, whether it's super conducting qubits, ions, or photonics. I mean, when we kind of, do that and build something, I think, it'll be really good. And you rightfully pointed out, I think each of these approaches has got its own advantages and its own disadvantages also. But I'm sure, like, I think, we are in this cusp of like a fantastic point of time. I think in the next few years, maybe this current paradigm, will possibly help us maybe discover new materials. Maybe the current paradigm itself, with artificial intelligence, maybe it'll help us maybe understand nature deeply, and maybe we'll be able to kind of simulate and build these machines. So fantastic. I think time that we are sitting in, and I think you're at the cusp of building something really really cool, because yes, I mean, the 6 qubit quantum computing, I mean, the breakthrough. So would love to understand more about when and how did you decide to build a photonic quantum computer in India, and what were the hardware and software challenges in building India's first 6 qubit photonic quantum computing system.
Stick photonic quantum computing. There are many approaches. One of the approaches is called continuous variable. The entanglement in that approach was formulated in India. There's geometric phases, which is also one of the important thing which evolved as quantum phases and everything. And some foundational work done in India. So there has been a prominent contribution in theory. So experiments, it happened at some point with some government meetings where they were talking about the possibility of quantum technologies, what all had happened. There were a lot of proposals. They tried to pick few people. There were very few people who had some background in the field. So that's how I got involved at some point. And it was I always like light and photons. And I said, okay, this is something which has not been touched. There is nobody who is trying to look at photonic quantum computing. And that's how I said, okay, let's begin with, not as a computing was not the first thing. It was almost like generating entangled photons, understanding them, and eventually build it to quantum. But now, if you say the 6 qubit, which has been, or like, it's not, I mean, okay, the use of word of first in India, first in all of these things, it's probably good for a tagline and thing, but for us, yeah. So, but as a researchers, we need to know what really it is, right? So, because there are certain global standards, but what we have also done is not nothing inferior, or like, it's not just that we are trying to catch up, but the theory for that. The model has been taken many years. It didn't happen overnight. From 2009, there was some problem which we're trying to work out how we can have universal quantum computation using a quantum walk model. And there's been, I think we wrote some papers in 2018, 16, 17, came up with mathematical model to have, because I said photons can't interact with each other easily. So can I use different degrees of freedom of photons to make them interact and make gate operations easier? So there was theoretical model which we had developed, mathematical framework for it, and say mathematically it is possible. Then those papers were published. A couple of papers were published to say look at the practical feasibility, but then how one has to do experimentally and how I can control photons degrees of freedom, that we started working on after we got the funding to set up a lab at IISc. And we step by step we started converting the mathematical model which we had developed at the Institute of Mathematical Sciences. So with my students I developed it, and then we converted them into an optical scheme in IISc, and we executed them step by step. So it's a long year. It's not just over. Like might be some of them say, "Oh, you set up a lab and very quickly you got something." No, okay, because we had clarity from many years of our work. There were two PhD students who had graduated building up a mathematical model, and there were two more PhD students who started entering into this. And there are many few postdocs who worked on optimizing the scheme, and then we implemented it. Again, is it when we talk about 6-qubit, what it can do is again a very important question. Right? We have generated a 6-qubit entangled state and we have implemented few gates, but that doesn't mean that we can do anything with that. So there is the number of gate operations limitation right now, and we are trying to improve on. So the next challenges are for us to increase the number of qubits plus the number of gate operations we can do. So to address some of the problems with this process.
Right, right. Yeah. So I think, I mean, the general narrative that goes out to the world is that quantum computer is going to completely change the world. It's the fastest thing in the world. But, when you understand deeply, then you realize that, okay, quantum computing has its own problems, and it's got a narrow use case at this point in time. Eventually, if we are able to kind of create error, error-free quantum computation, yes, I think then maybe we will start scaling, and then maybe there'll be like true applications that will be coming out from there. So my first question is, Professor, I mean, where do you currently stand with this quantum photonic system, and is this architecture scalable? Right now you mentioned that this is like a 6-qubit thing where you've encoded 3 qubits per photon using the Greenberger-Horn-Zellinger state. Where does this stand at this point in time? Is this architecture scalable? Can we scale
Yeah,
this?
so I think there's two questions I would like to answer. Probably one was not asked as an explicit question, but that's a very important question which I want to answer. Is that when we see what is the future, whether quantum computing is going to solve X, Y, Z problems, these are all like a very the questions may not even be relevant at this point, because uh, we all try to think of the possibilities depending on the problems which you see as problems. So I just have a very historic why sometimes history helps us, like around beginning of the previous century, not here, not now. In the 1900s, people had put up a challenge how the technology is going to change. Visualize what it's going to be in next 20 or 30, 40 years. And then when people look at after 40, 50 years, everything was wrong. We were far beyond than what it was. A lot of things which were not even expected, people never thought about it, was achieved. It's left to us a creative minds which is there. There are plenty of them. Our generation are trying to, like our generation, or probably who are exposing, are trying to see things in very pocketed way. Right, the generation which are very very young now today, 15, 20 years, they have grown up. They've seen mobiles, they've seen technology which is beginning with it. For them to even to explain how the world was when we are not able to reach, when we are not able, it's very very difficult. But their thinking and their imagination and what they want for their future is not easy for us to even imagine, because my trained mindset narrows down my thought process. My trained mindset narrows down what I have to visualize. So we might try to put 6, 8 big things what quantum computers can do, but I would just leave that open. Our job is to, as I said, create knowledge base, leave it for the next generation to take, and let them imagine and build on it. As long as it is honest, correct setup which you have built, that's going to take over and look at it. So that's why we should not stop just thinking in technology. The science and technology has to go hand in hand and create a knowledge base. That's first point. Now, I think the most important question coming to our research or activity. Yes, when I said when we were trying to build a mathematical model, the two important things. Yes, we had to address the issue of interaction because photonics gate operations were probabilistic because with certain probability they used to be successful, and we wanted to increase that to some extent that we could do it at a 3 and 6 qubit level. Now if I want to increase the number of qubits, then I need to involve more and more photons. Then it does become a little bit, it will just become probabilistic, but it will be better than any existing scheme's probability behavior. So, which means that it would be less probable than any known schemes. So, in that way, I would say it is better than the all the known existing photonic discrete variable photonic computation model. So, scalability, yes, it's scalable. Because that's what when we say if it's not scalable, then there's no point for us to build a mathematical model. Then I should say we have built some 4 qubit or 6 qubit system which is useful for some communication or cryptographic applications because smaller number of qubits have some applications there and they're still a useful tool, and I should stop there. But when we are using a word computing, then it means that we do have a scalable architecture up to in fact we have kind of worked out few up to 100 or something, and then it means that we can scale it up beyond that. How do we scale? There are multiple ways. Right now, in our purview, we are trying to use a combination of miniaturized bulk optics and try to scale up to 30, 40 to 50 qubit level and demonstrate few things because it's not just about the qubits, right? I can actually have a lot of photons and I can say I have a large number of qubits. I can also do that with photons, but that does not mean that I can do some operation. So we need to now what is our task for next year or two is that while scaling, demonstrate few algorithms implementation, few sample case that gives a clear architecture. Because when we mathematically build certain architecture, then we say, okay, this is how it works. When we try to build an experimental setup, then there will be some corrections to the mathematical model. And that we have already done at a 6 qubit level. When I have to take it to 12 qubit, next target for us is to go to 12 qubit. When I'm going for a 12 qubit level, then I might have to make some modifications to the skill to make it easier. So when I go for a next level, and these improvisations and modifications will help us to take it to integrated circuits later on, which becomes then we don't have to manually build such kind of thing. There can be a mechanized process of having integrated circuits built in a fabrication facility, and then scalability won't become a very difficult task. So again, as I said, we have to build now a knowledge base to fix some minor issues, errors, or corrections to the existing model. It would more or less be improving and making things better time.
Right. So, Professor, I mean, yes, I think you already mentioned that. I mean, when we get like a working quantum computer, the applications might be something that we are unable to imagine at this point in time. But will be great if you could, maybe give some kind of understanding. When you say that, maybe when you scale from 6 to 12 qubits, when you say that you want to demonstrate something, maybe it will be great if you could kind of give us a glimpse of like what could be those demonstration. What do you see the near field maybe terms of applications, and what could be will also be great if you could like push beyond and maybe imagine and give the audience like what could be those far out far term applications of quantum computing that you're very excited about.
What we have already shown with a smaller number of qubits, that kind of helps you to say like about 12 qubits or like other when we scale up what we imagine to do. So a simple 2 qubit system, what is it useful for, right? We can say, and I have a 2 qubit system. Why is it a classic a classical system can do many things? What is the usefulness of 2 qubits? So what we did with the 2 qubit system is to build a quantum random number generator. We actually built the devices which is currently being used in a few government organizations for their key generation. Now, what is this key generation? Why quantum mechanics is going to help you? It's a big topic there, but I'll make it very, very short. Today we get our OTPs. Today, all of us are dependent on some pins we are going to get. How are these pins generated? Now there is a software which creates the pin, and they're giving it to the bank. Now the software is a program which has been written. Now the program which has been written can actually be manipulated. Somebody can actually play a malicious role and give you a pins you want. But now, if I ask nature to give me the numbers, nature to give me the pins, then that's the most uncontrollable way. When we talk about wave particle duality in the beginning, there's a collapse of wave packet. It is spread, but only when I look at it, it is falling at this point, or else it is not. So I can't say if I'm building the device, I can't say where it's going to collapse. It is collapsing at one particular point. Even if I build a device and I give you, it is collapsing not on my programming level. It is nature which is deciding. Now, what we did was we took a two qubit system. Now, two qubit state would be, now I can convert them into a simple binary language. I can get 00, 01, 10, 11, the possibilities. Now, when we say it collapses to one of them, which means that instantaneously I'm getting it 01 or say 10, 11, any one of them. I don't have a control. Nature is giving these numbers. And now that were converted to OTPs or captcha code or QR code or what captcha or a QR code, and that's what we did with the two qubit system. And currently, it's actually being used by government agencies for their application. So that was the first. That's how we tried to test scalability. Now, when we went to four qubit, six qubit is the now, but then last year itself we had a four qubit, and we actually showed something else with that. Public and private keys we talk about, right, and our encryption and decryptions of the images. So we because when photons can be entangled, right? So I can take a four qubit system, two qubits is sent to one point, other two qubit is sent to another place. Now this can actually be treated as a public and private key. Now nature is giving this. I don't have to do any math. The natural way of the current cryptography language, where mathematics plays an important role, where these keys are generated by a complicated mathematical problem and hardness of breaking, factoring. You have a large number, you have to factor the two, one is given to one party and the other one only when they match, you are deciding. Now, this is a mathematically hard problem and it's defined by mathematics. So now people have tried to come up with very, very complicated mathematical complex problems so that we can use them for cryptography. But with the quantum physics, this nature is just simply giving me a four qubit system, which is replicating that behavior. And that's one of the device which we built. Like we are currently prototyping it. Because photons works in room temperature, the two qubit device, we actually shipped it around to different places. It went to Delhi, it went to some other place, it has been used. And now four qubit, we are making a complete compact prototype device which can actually generate a public and private keys for the users. So I'm just trying to say, like this, there are a simple four, five, six qubit, the immediate applications. Because at the end, if the government is investing a public funds on research and R&D, we also have to show that there is some immediate usages. Because long-term usages, we might think of many things and something else might come out, but immediate usages are very, very important. That's some of the point. But now, the moment we go for 6 to 8 qubits, there are some simple natural dynamics which can be a simple chemical complex interactions or some things, which we would like to model and say simulate them explicitly. Classical computers may do that problem, but that if we show that we can actually define it also a quantum algorithm, then it establishes that this algorithm is valid. Then one can build an algorithm for a larger complicated complexes and keep looking at it. So, when we are scaling up with every smaller number from smaller number to larger number of qubits, we are envisioning certain problems like this. But clear said and done is the security applications where there's a clear winner at the smaller number of qubits. I think this and photonics is tailor made for this. Other hardwares, you can't carry a cryogenic superconducting qubit systems to do that, and it's also very. But this photonic system and photons travels. You don't have to superconducting qubit sits at a physical position. It won't travel. So photonic qubits can actually travel. So I can create qubits there. I can send them to different places and then look at it. So that's why I say photonics would leave. There is no way that you can take light out of your picture of quantum world. the light is there in some or the other way, and it's going to play a part because it helps us to move around different places. These are some of those few small scale applications, but when it comes to a big imagination problem, I'm not going to talk about what industries thinks about it, what the economical world thinks about it. For me, my personal passion has been simulating nature, the complicated behaviors in nature. When you said you can, use your imagination, for me, even black holes is an imagination, right? If my physics is correct, if the quantum mechanics is what has helped us to understand what's happening at the black holes, field theory, then I should be able to mimic them in a laboratory situation, right? So there are few things. In fact, there's one interesting problem which I did in collaboration with Maryland, the smaller ion trap system. It's a relativistic dynamics, which we call Dirac equation. I developed an algorithm in the Institute of Mathematical Sciences. We worked in collaboration with University of Maryland. Today, it has spun out of IonQ quantum computing, a big company. But with that, we implemented this algorithm where in a laboratory setup, we showed some relativistic behavior. Relativistic dynamics happen at the speed of light, but we could mimic them using the quantum qubits and quantum algorithms. Now, if I do it in large scale, then I should be able to mimic some of the strangest, the most complicated or the highly fascinated things like black hole, or we call, I mean, I don't want to use the word like time travel and few other things, but because there is, but of course, everything which quantum physics defines, the most complicated to the edge of what we understand the universe, we should be able to mimic them at some point. And that is what I see might not be 10 years down the line or 40, 50 years down the line, our future generations will accomplish with the most complicated quantum machine that's been built.
That's so very cool, because I guess, and I mean, most of the time, I think the startups, the startup community, as well as the researchers, they get trapped. They start with a big vision, but then they get trapped by the economics of things, like, okay, let's kind of, build things and build a product first, and then what happens that maybe then you lose out the vision. I'm not saying that the product is not important. I think the product is the key, because I think whether it's a startup or whether it's a researcher, you need to create things which are sustainable. But I think, these crazy visions of doing research, which can someday maybe be able to maybe kind of, take a glimpse on who we are, why we are, what are we, and these big questions like the black hole. I mean, if we are able to simulate, I think the world completely changes. The things that we will be able to do, like you mentioned, I mean, and even the time travel or whatever, I think, because I think the entire universe is quantum mechanical, and if we are able to maybe simulate nature, the kind of things, the kind of applications that we'll be able to kind of build will be humongous. Like, just to kind of give you an example, I think there was two startups in the world. I mean, maybe just 15 years back. One was OpenAI and the second was DeepMind. I think they started with this audacious goal of not creating artificial intelligence for building applications, but, creating research, and with the larger goal of building a general purpose machine, a machine that could maybe simulate intelligence itself. And at that point of time, they were ridiculed, But right now, if you go to see, they are the most valuable companies in the world. So kudos to your belief and a vision, and more power. And I wish there are more researchers in India who think big. Professor, are there any quantum photonics breakthroughs that has caught your attention? Because recently I read about quantum, talking about like maybe like a million photonic qubit goal, and then there was this chip X from China, which is built like a photonic chip, which is they claim that can push AI tasks 1,000 times faster than these normal NVIDIA GPUs. Are there these photonics breakthroughs that's caught your attention?
So I'd see two things. Yes, I mean, if you're looking at PsiQuantum or anything, I mean, actually, I know from the group which ended up becoming PsiQuantum as an academic research group, they had a knowledge base. What I was said is creating knowledge, right? About 15, 20 years of extensive research work of controlling photons, learning about it. When they decided they want to have a startup based on this knowledge. Of course, the challenges, as I said, the interaction challenges existed, but they try to bet on it at that time, even if there's less probability, because I can generate thousands of photons, millions of photons. I'm going to lose some photons. It's okay, right? Because when I have an access for it, I can always lose some of them, and that's the way they began with. But when the company started, when they started working on, they themselves add knowledge base, adding into it, where they're trying to come up with some what we call as a cluster states or some additional, new techniques have been introduced, and they're talking about millions of qubits. So what I said in the when we look at our architecture, whatever it is, once you have a clarity of how we are building gates operations and then the photons are moving, and the scalability is not at all a question with photons because they are robust against the environment. The environment don't just come and destroy them. They don't have noise coming in like the superconducting or other hardware where qubits are very clearly sitting in there, but the noise is coming. That is not there. That's why they are just talking about millions of qubits. So I see that they have, of course, as I said, there are certain challenges for that as a company, as they have big investments. Of course, they are aware of those challenges, but I think they are also practically working towards some targetable role. But when you talked about breakthroughs, I think I would actually see there's some other one other experiments. There are very few experiments which has actually been done to show what no classical computers can do till date, right? So there are some claims of supremacy some time back, but with Google, but that they actually had to it was shown that does not. But recently they have shown that's fantastic, because it's a smaller number of qubits you look at it. But the other one which Chinese group showed was called as boson sampling experiment. They did it with about 72 photons on an average, but it had some 100 plus photons, and they looked at it. But now these experiments were already done at a small scale by few universities in 2009. They did it with 10 photons, and then they showed that how you have multiple photons, they behave in certain way. It maps to some complicated mathematical problem. I'm not going to go deep into that problem, but it showed some operations, some results which no classical computers can simulate it with 50. But that I still think is a very, very good result, because today also it's upwards. It's not even in universal computation. It's just as one specific task which it showed. Now I can imagine if I can make it universal, what all I can do. I mean, there are 70 photons which are going in, and now I can't control them. They just go, they interact with one specific base, and then you get some results. I can only make certain missing and certain fill in. That's all, right? That itself could show something no supercomputers in the world can do. Then, if I can engineer them all at every stage and then look at it, that's what we call as universal computation. I can do gate operations. Then I would open up the whole pool of possibilities with it. So I see it as a very good experimental demonstration, but that took them many years, right? 2010 was the first time they showed that something can be done in a very small scale. They showed it took them 8 years for them to build that massive setup and result from China. So that kind of says that there is a lot of hopes and promises and promising results which are coming at every intermediate stages. There are many small results which are coming up, which would say, I know photons moves faster, but they can't have a memory, you can't store them. But there are certain intermediate things, which small results are there, which one has to try out whether that's going to fit in or not. And people are working across the world to address some of the problem. And there will definitely be a solution. That's how I strongly believe. I know, because if there is a problem, there is a solution. There should be some solution. But how long it would take, or we should come up with some other argument, some other logical construct to say why you will not be able to find a solution. I mean, if that is open, then it means that you have chances for it to, find a solution and to look at it. Now, possibilities of problems are immense, right? And when people talk about drug discoveries, I don't ridicule it. That's the most important first problem which we are talking about. Because when we are talking about two or three particles, we had done some simple algorithms to talk about electrons propagating on some chemical. It can be a benzene ring or any of those kinds of things, right? Now, when we try to model them, when about 40, 50 atoms coming together, then the electrons behavior, they're entangling with them, and there's a lot of interference superposition happening with that 40, 50. atoms. Now, this itself is a very hard problem for any supercomputers can to do. 50, what we call as 2 to the power of n possibilities. And it means that if I'm having just about 50 atoms, and then all the electrons of each atom could interact with any of them, then 2 to the power of 50 possibilities can come out. Now, that is actually already hitting the limit of the best of the classical computers bits we are talking about. So now, if I have about 100 chemical, atoms interacting, then no classical computers today can simulate them. How do people do simulations today? Quantum chemists do a lot of simulations. How are they doing? Now they are breaking down the problem into small subsets. They're solving them and then they're putting them together. Now, when we are breaking them down, what is happening is that when we talked about superposition in quantum mechanical system, which means that now I'm breaking them into the problem, which means that I'm actually cutting down the quantum interactions between those subsets. The moment I am cutting down, I'm losing a significant amount of information there. So, which means that I'm approximating. So, any chemical complexes dynamics or simulations which people are doing, they are parallelizing the problem because it's very hard. No computers can do existing computers. So, the moment you are parallelizing them by breaking them into subsets and putting them together, you have done a good amount of approximation. Now, in that approximation, some wrong results have got into, some useful things have gone out. Now, that is what is actually now this approximation is helping me to design the drug against some problem. Because there's some biological body entities there. Now I have this chemical which has to react and solve a problem. But now my simulation has given me something which is not exactly correct. It has its component, but it also has something unwanted. Something wanted might be missing. Now, this is a very well understood problem, and that people know that. Very efficient quantum computer which can simulate the large chemical complexes efficiently, then whatever output I'm going to get as a solution to the problem will be an exact solution. It would be like I'm pinpointing my problem and I'm finding a solution for that. I'm not just beating around the bush. Of course, beating around the bush does kill a snake up many times, right? But it also destroys the surrounding around it. But now that's something which I see is the most important problem which can be addressed, as an immediate, which can directly impact humankind, along with my fascinated problem of simulating the complicated universe, right? Because it's not about time traveling or doing any of those wonderful technology thing. It's just understanding. It just amuses, sitting here, with just some little bit of math and then trying to understand the world. We are talking about how the universe were formed. We are talking about how the black holes are formed. Now, that itself is fascinating enough. Now, if I can mimic them at a small scale, then we just have to be happy there to see how we've been able to understand something about the nature to the correct form, right? So it's we might be missing many things. It's not that we understand. Might be it will also help us to fill the gaps. Even quantum physics, there's a lot of it's experimentally we understand some things and we are building some things which we can't observe with the logic. Might be something else might come up to understand them, to see them, right? So it opens up a big.
Professor, my last question to you. I mean, India is pushing its quantum mission, with the India National Quantum Mission. What excites you most about this initiative, and how supportive has the ecosystem been in helping you develop this quantum system? That's my first question. My second question is, I believe that there's a lot of developer ecosystem here in India, like specifically in quantum developers. What would be your advice to those young researchers who want to get into the field of quantum computing and development? Where do they start from?
Okay, so I think the first question, I think it's been fantastic, the National Quantum Mission. In fact, I should say before getting into National Quantum Mission, I think DST had already had a pilot model which is called Quest, Quantum Enabled Science and Technology. I don't know what we call a small pilot projects were given for about 51 researchers. I was also part of it. There I was looking at theoretical as well. So at that time, we were all contributors for the first draft of a National Quantum Mission. First it was an academy. It was actually academia, which was asked to come up with what are the possible problems, and that draft later on was taken around the government organizations, can be DRDO to space organizations, everything to give their input, including the end users like army defense. So they also gave certain inputs of what they want. So it is a very collective document, which later on became a national quantum mission document. And that really, I mean, there's nobody to say that not involved. Academia was involved. All the government organizations were involved to come up with what India has to vision. Right? It's we are all contributors, right? So it's people's. I should say people. I mean, of course, we have billions of them, but people who are working on it, most of them have played a role in coming up with that. Now, execution. It did happen. Okay, because there was an announcement at some point, and then we had to follow certain rules. Right? It can't just be said, okay, there is a money you take around and then you play around with it. I know it's a public fund, and there is a course which has to be followed, how to disperse them. Everything is accountable, right? So having followed that, the best thing was last year was the calls announced, right? So though there were people who were working on it, everybody had to compete. So the last year, February, March, so the calls were there, and we were given certain deadline, and we were told by August, September, the decisions will be made who are going to lead the certain. And surprisingly, and for the good, it happened on time. That's something which, because it is not easy task to find reviewers, have evaluations of hundreds of people who are submitted, because there are a lot of submissions and everybody has to be evaluated. The budget has to be looked into, and finally it was approved last year. And early March this year, February, March, we started getting some funds, and it's been very right now I think we have got funds released for the first year, whatever we asked, what we need for the first year, because procurements, there are certain things, ecosystem is very important. Like, I'm bringing in your second question also to the point here, like, if you say there are some funds you have to build, then you can't try to build everything from scratch today and then say I'm going to do it. I mean, we need to first reset, first build what exists, what we can also procure, and then build certain things, and then start building the ecosystem at the ground level, involve startups, involve industries, involve other government organizations. So the ecosystem has to be built, and this has been planned under National Quantum Mission. The IISc Quantum Computing Hub, or IIT Madras Hub, or Mumbai Hub, or Delhi Hub, or there are four hubs which are set up. They've been tasked, or they've been asked to now look at the startup ecosystem, the involvement of other small players, so that you bring them all to build certain required smaller components to our bigger system which we are building. So it has all been started very well now, and there are funds for us to begin with as we requested. Of course, procuring, we have to follow again government procedures, right? So the bidding has to be done, and when there is an accountability, when there is public funds, we have to follow rules. There is some small delays, but that's fine. That's how it has to be, right? So that everything is intact. So it's yeah, we have been since we have got funds, we have built a new lab now already. In the sense we have because earlier labs were small, where we had our 6 qubit. Now since we have to scale up to larger number of qubits, we need a bigger space, and so that we can build, and all those things have been in place to go ahead with it. So it's been very supportive, I should say, at least as the funds wise. And it's we. In fact, when I say academia is involved, and the people in DST who are working closely with us. So we have right now, over last 1 year, since we have been interacting at multiple levels, it has become a part of a group. We have our own disagreements. We have our own arguments. We were sometimes unhappy with certain things. They are unhappy with certain, because as you said, when there's a public funds, their expectation, it can't be. They need deliverables, right? That's how they can account when the money is coming from the public funds. You show us deliverables, we show us used products at the end. And that's what probably we might say that, of course, science, fundamental science is very important, and we also have to explore it. No, we have in the middle path, they don't stop us to do our science. They're not stopping us to do, but of course they expect us to do some deliverables. Now it's a task for us as a researchers to see how we are going to balance, because our long-term interest of building knowledge base should not be compromised in parallel to delivering what is intermediate deliverables needed to convince both the government and the public, who are trying to see that quantum is going to change, that some outputs are there which can be leveraged for it. Now, coming to an ecosystem, I think there's a lot of the word quantum has been buzzed around, right? Everybody talk about it, and everybody would say, "I'm going to." But people want to start should be very cautious here. It's not about just putting up things existing together, or just not adding about some additional software to things which exist. So it is still deep tech. You really have to know, when sometimes students come and say that, and I try to look at some softwares which trying to look at some algorithm, and I have some expertise. I said, no, first you also have to understand what is happening at the background, because as you said, no architecture is established, no hardware is established, so which means that you need to know what is at the background. Only then any small change will be adoptable. If a startup today is coming without without a vision of how they are going to adopt to time, like I can say that I built, for example, if I say I build one particular device which gives some random numbers, and I say, if I'm not thinking of how I'm miniaturizing, how I'm using a new quantum resources which are like new quantum ideas which are coming into the system, then I'm dead there, because somebody else will come and play an important role. So they have to enter the domain with a long-term commitment and vision. Then definitely there is going to be, because the knowledge base, even a startup is going to have, is irreplaceable. Nobody can, probably after 10 years, 5 years down the line, somebody might come with huge investment, but they would still not have all that knowledge which people would have accumulated over the time of time. So that should be the focus. They can have a startup, they can build a small components, whatever it is, but they should start thinking it like building a small R&D lab there. Right? It means that they are having some research associated with it, and that is the knowledge base which the startup can actually be a big player in a long run.
Right, Professor. Really, really appreciate you taking time and being part of the podcast. Like I mentioned earlier, I think we're sitting in a fantastic point of time. I think the next 10, 15 years is going to be super awesome. The entire, the paradigm of the computation was zeros and ones. But here we are, we are, I think, transitioning, and we're going to that special place, like another place of sorts, where we kind of go down, to, compute with qubits, the source code of life, like what we are all made of. And I think, over the years, I think India has been, leading in terms of software. And I hope that, it stands up and is counted in this new sort of realm that we are getting into the quantum computing space, And I think, the push by the government and researchers such as yourself, taking or being counted and building these new things. Kudos to you all, and I hope that there's more collaboration, because earlier it used to be only just maybe all the breakthroughs used to happen in US or China, but right now I think the world is changing, and India has also been counted, so I hope this kind of moves forward, and we really look forward for seeing like the next breakthrough of quantum photonic technology coming from India, and powered by India, from possibly your lab, So really, really appreciate you taking time and being part of the podcast. And to my listeners, if you like what you see in here, then please press the subscribe button. Until next time, see you guys. Bye-bye. Thank you, Prof. Really appreciate this. Thank you.